Failure mechanisms for tunnels in rock, presented by Vishal Patel and Haitham Daoud for Geological Engineering class taught by Professor Matthew Molden at Virginia Tech in fall 2011. The outline of our presentation will be the introduction, the potential causes and failure in tunnel along with failure mechanisms, followed by conclusion. We'd like to begin talking about the tunnel collapse by referencing few very true quotes. As Sir Michael Latham once said that no construction project is risk-free. Risk can be managed, minimized, shared, transferred, or accepted. It cannot be ignored. This is all very true for tunnel construction, where an error can have a major impact to the project and lives of construction workers. So whenever tunnel is constructed, the risk that comes with it should not be ignored, and everything should be done in order to minimize the risk. Another important quote by Gallagher states that tunnel construction is one of the riskiest insurance fields. When an accident occurs, it reaches catastrophic proportions. Again, these quotes emphasizing on how tunnel construction is one of the most risky fields to be in. So what is a tunnel? A tunnel is a passageway completely closed except for its opening at each end. Tunnels are usually used for transportation of car, trains, and liquids. They're constructed through mountains, below waterways, or underground in metro areas and have massive economic impact. Tunnels allow for faster and, in some cases, safer routes to a destination. Tunnel collapse plays a major role to safety of our infrastructure and, more importantly, the safety of the public. Tunnel collapse can be defined as a breakage of material from tunnel perimeter resulting in change of tunnel cross-section. Tunnel collapse is dangerous on many levels to public and existing infrastructure. The wide range of potential failure causes and failure mechanism is partly the reason why the risk associated with tunnel construction is still high. Thus, in this presentation, we will discuss potential geological causes of tunnel collapse, followed by a comprehensive list of failure mechanisms of tunnel excavated in rocks. Several historic cases are also being presented in relative to the associated failure mechanism. With construction of any tunnel, there is always a risk of failure due to human errors and unknown geological formations. While human errors consist of miscommunication, calculation error, not following safety precautions, or bad project timing, human errors can be minimized through improving on past mistakes or not making them. But geological heterogeneity is tougher to predict and handle because they can happen on massive scales. Weathering, folding, and groundwater presence can alter the behavior of rock mass around the tunnel, making it incomprehensible. Weathering of rock mass through water or air can affect at great depths and decrease the strength of rock. Water flow through faults and joints can erode materials between two masses, making them loose and susceptible to failure if tunneled through. Faults and folding of rock mass can have high and low fluctuating stresses over a geological map. Faults and folds are hard to deal with during construction of tunnel due to rock bursting under high stresses. Groundwater can create hydrostatic pressure near the face of wall if it has not yet burst through. It can also form karst if water is present near soluble rocks such as limestone, can create cavities in tunnel which leads to failure of rock mass near fracture and joints. Study conducted in 2006 shows that following number of tunnel failures during past several years. In many cases, tunnel failure caused delay of work, redesigning of tunnel, change in construction method, or creating a bypass tunnel around the failure zone. Whenever a tunnel failure occurs, there is a combination of one or more failure mechanisms associated with it. Failure mechanisms such as loss of strain, squeezing ground behavior, rock bursting, failure related to tunnel and fault zone, and inrush failure will be discussed. Loss of strength can result from blast damage through creation of new fracture or expansion of old ones by explosives. Although blasting is specifically designed to create fractured rocks for an easier method of excavation, the impact from blasting may occur outside the tunnel radius, permanently reducing strength around the tunnel perimeter. The exposure of some rocks to water or air can lead to weather decomposition, which leads to loss of strength, resulting in failures and construction delays. The Winterwald Railway Tunnel extension in Vienna, Australia is a good example of failure due to water interaction with rock mass. During construction of the tunnel in a flint zone, isolated water buildup in certain layers of rock were exposed when workers drilled boreholes for roof bolting. Water was exposed to sandstone due to the pathway created by borehole, and the interaction of water with sandstone layer caused compaction and loss of shear strength due to increasing void ratio. Thus, the failure of tunnel was unavoidable due to loss of shear strength and increase of pressure around the tunnel.
Squeezing rock slowly advances into the tunnel without perceptible volume increase. Many geologic environments result in squeezing behavior. Yacambo Quibor Tunnel, located in the Andes, Venezuela, is a good example for the effect of squeezing rock on tunneling. This tunneling project is considered by many as the most difficult in the world. The squeezing rock trapped the tunneling boring machine in 1979, and its remains were removed years later. Some sections of this tunnel was completely closed by squeezing rock. Rock bursting. The rock bursting mainly occur due to the redistribution of the stresses due to the excavation of tunnels. Many factors contribute in the occurrence of rock bursting. For example, the mechanical properties such as density, porosity, permeability, and strength of the rock. The geologic structure, such as the joints and folds in the region. The tunnel's size, shape, and orientation. Also, the stress in rock is an important factor, as rock bursting generally occur in regions of high stress concentration. The figure shows the different failure modes in tunnel as a result of the bursting rock behavior from left to right. The first figure is a compression failure, the second is a punching failure, the third is a combined bending and thrust failure. Failures related to tunneling in fault zones. In general, tunneling in fault zones is difficult and challenges. Tunneling in fault zones is generally associated with substantial construction delays, sudden failures, widening of tunnels, and concentration of high stresses on the lining. Tunneling in highly fractured zone and crossing interfaces between geologic blocks are the two different subcategories associated with this failure mechanism. Highly fractured zones have a low Q value and small stand-up times. This figure shows a typical failure in highly fractured zones. The rock suddenly fall down, trapping the boring machines and widening the cross-section of the tunnel. The channel tunnel is a good example of tunnels that pass through highly fractured zones. The channel tunnel is a 50-kilometer undersea rail tunnel linking Folkestone, Kent in the United Kingdom with Coquille, Pas-de-Calais in northern France, beneath the English Channel at the Strait of Dover. Tunneling in the fractured zones slowed down the advancement rate, resulting in substantial construction delays. The regular advance rate was about 334 meters per week, while in disturbed zones it was as low as 127 meters per week, which is about 38% of the regular advancement rate. In an extremely disturbed zone, the advancement rate was about 8 meters per week, which is only 2.4% of the regular advancement rate. Even with substantial construction delays, failure was avoided. Another example is the Evinos Moronos tunnel in Greece. In this case, 10 meters of rock above the tunnel boring machine fell down, forming a large cavern. As shown in the figure, the cavern was grouted. Then the boring machine continued its advancement after the grout set. This resulted in 50 days of construction delay. The delay could have been more serious if a larger cavern formed. In this case, failure was unavoidable. The inrush failure mechanism occurs almost instantaneously. As shown in the figure, this failure occurs when the tunnel gets in contact with surface water or unconsolidated soil deposit during construction. It results in a sudden inundation with a mixture of water and soil and result in a substantial number of fatalities. The current investigation aims to present the main causes of failures and the failure mechanisms associated with the construction of tunnels. The following are some conclusion remarks. Geologic investigations are the cause of a lot of problems associated with tunnel engineering. Hence, care should be taken in performing such investigations, and uncertainties associated with these investigations should be carefully evaluated and considered. Learning from previous mistakes is important. Hence, the large list of failures database in tunnel construction is an invaluable resource that should be extensively used during the design and construction of new tunnels. Tunnel engineering is usually associated with a lot of uncertainties and risks. Hence, all possible case scenarios should be studied and evaluated carefully before and during the construction phases. It's important to constantly monitor the behavior of the tunnel during and after construction, because failure can occur at any time. Emergency plans must be prepared to be adopted in case of any sudden problems. Tunneling projects are generally very large and involve many parties from different fields at different stages of construction. The communication between these parties is critical for a successful tunneling project. These are the references. Thank you for your attention.